Okay, so in this last video of this chapter, magnetism and matter, we will cover the portion from magnetization and magnetic intensity. In the last video, we studied about Earth's magnetism and Gauss law, and then we studied about how Earth's magnetism is present, what is magnetic declination and dip. Before that, we did about electrostatic analogy, then about how bar magnet is there, and then this is the introduction. This chapter is pretty small, so it's almost fine. There won't be much numerical, just concept based questions, and this part is probably one last derivation and the other is just theory part, this one, except this few formulas which I'll just tell you about it. So we'll start with magnetization and magnetic intensity. So this topic is divided into two, magnetization and magnetic intensity. So first we'll talk about what is magnetization. Magnetization means the total magnetic length, the total magnetic strength per unit volume is magnetization. That's it. So magnetization refers to total magnetic strength per volume. That's it. Volume means surface area, same thing you can say about same thing. Okay, that's it. So a net magnetic moment which is non-zero, we define magnetization of a sample to be given to its net magnetic moment per unit volume. That's it. And then it says about that it's a vector quantity and its dimension is L inverse A. A is because of M and L inverse is because of V, and it is measured in AM inverse. And now we'll talk about magnetic intensity. Okay, this is a portion where magnetic intensity starts. So basically we will start with magnetic intensity. So magnetic intensity refers to the net magnetic field experienced by the substance. Okay, so if I take one object, okay, if this is one object, okay, if this is one object or a magnet, okay, or a current carrying conductor or a current carrying conductor. Okay, let's take this as current carrying conductor because then it will explain us in more, then I can explain in more stuff. Okay, so this is a current carrying conductor. Okay, so this current carrying conductor will have magnetic field, right? We know when the current is passed through, magnetic field is there. So this current carrying conductor can have magnetic field represented by V, and this can be in two ways. Okay, what is way number one? Way number one is if I let the current pass through this, if the current is passed through this, right? When the current is passed, what magnetic field is generated? So I can say by current, because then it will generate magnetic field. Or what can I do? Or I can keep one magnet over here, right? North south. If I keep one magnet over here, again this will experience magnetic field, right? Before it was experiencing magnetic field. Why? Because of its own current. Now by external object, which is magnet. So this will call as internal magnetic field. Then this will call external magnetic field. Okay, so internal magnetic field is represented by I and external magnetic field is represented by H. Okay, now what is the total magnetic field experienced by this current carrying conductor? It will be the sum of this and this, right? So it will be the sum of the current, of the magnetic field made by this plus the magnetic field added by this, right? So B, which is total magnetic field, will be what? proportional to h plus I, right? So if I remove this proportionality, I'll get the constant mu naught, which is easy. So this proportionality is mu naught, so it will be mu naught h plus I. This is to find net magnetic field inside the conductor, or like for a conductor, the total magnetic field experienced. So yes, we found this derivation. Maybe you still have doubt. So in simple way of explaining is, look, this is a current, this is a rod, okay? Current is passed through this, okay? Current is passed through this, right? When the current is passed through this, there will be magnetic field, right? Because what? Because why? Because current produces magnetic field. There will be current will produce magnetic field, right? That's the internal magnetic field, right? So that's one. And the second one is if I bring another magnet to it, north, south. Okay, so first, because of this current, there will be one magnetic field going through, okay? There will be one magnetic field going through like this, like this, right? Because right hand thumb rule. What did I say? The right hand thumb rule I covered in one of the last videos. I said if the current is the thumb, then the curling fingers is the direction of current. So now it's coming from behind, from behind to up like this, right? So from behind to upwards like this. So this is one magnetic field it's experiencing, right? What if I bring this magnet near? Will this magnet will also make some magnetic field like this, right? We'll ignore the direction and all the laws, but I'm just explaining you. So now there are two magnetic fields, right? One is because of the current, second is because of the object. The one because of the current is called internal, and the one because of the magnet is called external. Why? Because we bring in an external substance or object to increase the magnetic field, okay? So this total magnetic field by current and by magnet in this place is B net, okay, or net magnetic field, okay? And we know this is proportional. Proportional means almost equal to what? The sum of this, right? If this is h, this is I, it will be almost sum of this, so h plus I. And if this proportionality I make it into as mu naught, it will be B net is equal to mu naught h plus I. This is it, okay? So now now this is one formula, okay, one formula done. Now the second one, next topic, I mean like in this next topic. So now look, we are adding this, right, for the total magnetic field, means they are almost the same direction, right? So now listen, we know for a particular object there'll be a fixed magnetic field, right? Because no matter how many iron wire you take, it'll have same magnetic field, almost like same way of getting the magnetic field, right? But what if this, so that's I, right? That's I. So the magnetic field which will produce by itself will be constant because it's same material, so it's same thing, okay? But this h, can I make this h variable? What if I make this magnet into big size? Then there will be more magnetic field. Then because of this more magnetic field, this I will be more. Can you relate it? Why? Because if more magnetic field is there, then there will be more magnetic field. If there's big magnet, then there will be more pole strength, means more magnetic field, okay? When there will be more magnetic field, it can make this I into more. It can influence I, right? Because if the magnetic field of the magnet is more, then it can definitely influence I, okay? What is I? The magnetic field of this iron rod, okay? So can I say H is proportional to I? Because this is external, this is internal. When I put more external force, there will be more internal force. We know that, right? If there's more external force, then there will be more internal force. Similarly, if the external magnetic field is more, this can influence the internal magnetic field to make it into more. So can I say H is proportional to I, or same way I is proportional to H? Any way I can write, right? So now if I remove this proportionality, I put one symbol X. Okay, X. Okay, so can I write I is equal to X H? This X is called magnetic susceptibility. Okay, so this magnetic susceptibility. So what is magnetic susceptibility? Okay, so first we know internal is proportional to external, right? Because if internal is increasing, then obviously external is increasing, right? So now if we remove this proportionality, we get this constant called magnetic susceptibility. Okay, so what is this magnetic susceptibility? So this is a constant for every material, right? So this is constant for every material, and it depends upon the temperature and the medium, what it is. Okay, like what the material is made of. This will tell us if this magnetic susceptibility will tell us if the object is high magnetizing, low, or low magnetizing. So this plays an important role in magnetizing. If magnetic susceptibility is positive, then it is magnetic, and if it is negative, then it is not magnetic. If the value of this magnetic susceptibility is positive, it's magnetic, otherwise it's non-magnetic. Okay, so now what if I use this formula in this? What if I substitute this formula in this? Okay, so if I substitute, okay, so I'll write B net is equal to mu H plus this H, right? Now can I take H outside? So H1 plus bam. So I get this now. Okay, so now I got this another formula. Okay, so this is magnetic susceptibility, this is external force, and this is mu. Okay, now listen, what is mu? What is mu? This is the free space of medium, like through which the medium, like permeability. What is permeability? It is the constant, or it is about medium, like air medium, vacuum medium, like that. Okay, this is about that. You don't need to worry about this. Okay, so this is the formula we got. Now okay, now what if I'm taking this inside the medium? Okay, this is for the total. Okay, so for inside the medium, this is for total. Okay, so for inside the medium, H is not influenced, basically, right? We know that H is not influenced. Why is H not influenced? Because we're talking inside, not external. We're talking about inside the medium. So for inside the medium, B net is equal to mu 1 plus, this is the for inside the medium, B magnetic field net is, this is the formula. Okay, and similarly for outside or for medium, B is equal to mu naught H. Same way. No change, no nothing. Okay, no change, no nothing. Why? What if this object was missing? If this object is missing, okay, then do we need to take magnetic susceptibility? What I mean is, in this formula, what if this object or this rod is not there? Then only this magnetic field of the magnet will be there, right? So do I need to add this? No. Then what is it? Mu H. Same way, that's it. That's from this chapter, from this part. So now if I take the textbook, here's what magnetization. Then over here they started with solenoid. Okay, because look, this is solenoid. They used a better example, solenoid. Solenoid will have magnetic field going like this, right? And if I'm bringing one magnet over here, this will also make magnetic field going like this. So now is the magnetic field increasing because this was 1, this is 2. Now total inside this will be what? 1 plus 2. Same way, B net is equal to B naught Bm. B naught is due to solenoid, Bm is due to magnet. Okay, now we this relation I'll say you don't need. Okay, let's start from here. Okay, so I thought that B is proportional to H plus M, this plus this, so B is proportional to H plus M. M is for the solenoid. Okay, remember that. So B is equal to mu H plus M. Got this? They used M, I used I, same thing. No worries about that. Okay, then they got this. Okay, now I used what is magnetic susceptibility. It is dimensionless, quantityless, and it is called magnetic susceptibility. It is a measure of how magnetic material respond to an external field. Okay, if it is small and positive, it is paramagnetic substance, means it conducts less magnetization. But if it is small and negative, then it is diamagnetic, means it does not conduct magnetization. And if it is higher and positive, then it is ferromagnetic, which is very strong magnet. Okay, so okay, yeah, this what is, so did I use this formula? Wait. Okay, yeah, fine, I'll delete this. Okay, so B inside the magnet. What is inside the magnet? Inside the solenoid, what is the magnetic field? Mu naught Ni, right? Inside this is the formula, right? This is the formula. So what if I have to remove this number of terms? Can I just write I? So is equal to mu naught I, right? So this magnetization M is expressed by, okay, so now this magnetization, or the magnetic field inside the solenoid is mu naught M, means mu naught into magnetization. Or what is magnetization? Total magnetic field in that volume. Look, definitely if this is one shape, to find the magnetic field total this, of course what will do, magnetic field in this divided by its volume, right? Same way over here, what I did, I took the total magnetic field, okay, and I multiply by its permeability or in the medium to get for the solenoid. Okay, same way I did for this. So when I added, I got this. Okay, first I did for this, I got this. Then I did for this, I got again mu naught H I got for BO. When I added this, I got this. Okay, so now H is called magnetic intensity. Okay, means which is by this magnet, and then it is equal to B by this thing minus M. Like I just derived it over here. Okay, over here. Okay, so what, B net is equal to mu naught H plus I. Can I take this over here? So B is equal to mu naught is equal to H plus I. So can I write H is equal to B mu minus I? Look, minus I, same thing, and then they go to this formula. So this is all division of this. Now this is still here, you can understand easily. This will also, if this I is not there, then it is H. Okay, now this portion is called relative permeability. What if we have to relate between two magnetic field of two materials or mediums, or yeah, of two mediums. Okay, so first, if I take in vacuum, magnetic field is what? Mu naught H plus I, right? Total magnetic field in vacuum is what? Mu naught bracket H plus I. But it's in vacuum. Is there any object? No. So this I can call it as 0. So so B naught is equal to M naught H. That's it. And then mu naught is equal to what? B naught by H. This is for vacuum. Now for air, definitely we can cut this because air does have some magnetization power. It can be influenced by any other object. So we're just taking for not air, any other medium. Okay, any other medium other than vacuum. Okay, so now B naught is what? We can take this mu H1 plus this. We took this. Now can we take this as constant also? Because this is a constant for air, right? Because I mean for any other medium it is constant. Okay, like this will never change, and this will also not change, but like this can change because if I put the outside magnetic field has 5, it will change. 6 has changed, 7 has changed, but this won't change. Will this change? No. So can I give this another constant, mu r? Can I? So if I give this mu r, will it be B naught is equal to mo m r h? Can it be? Right. So this total can I give as mu m h? Now can I write mu m is equal to B naught by h? I don't understand. So for air, what is it? This I found this from here to get here. This is constant because this is constant for any material. So I took it as m r, mu r. So I took mu r, mu naught, mu r h. So this is definitely constant. So can I give this one name, mu m? So I took this mu m h is equal to, so I got this formula. Then I took this h to downside, it became mu m is equal to B naught h. Okay, now no, this is main thing. This is now relative permeability, means comparing. When I compare these two, mu m by mu o, what do I get? B naught by h, B naught by h. Okay, simple. Now cut, I get B naught by B naught. Wait, B naught by B naught. Okay, yeah, but we know here it will be different, here it will be different. Why? Because this is in vacuum, this is in air. So I can take as B naught, this I'll take as BH, I'll take as BH. So here also it will be BH by BO. Okay, BH by EO. HH is common because why it is common? Because we took same magnetic field, like external magnetic field we took it same, but for BH, which is total, will be different. Why? Because in M, because in mu m, which is the second case, we are using any medium. Okay, so for medium, of course, it will be more than the vacuum. So we got this. Now if this is one way of relating. The other way is, instead of taking B naught h, I take mu naught and mu naught m. So mu m by mu naught. What is mu m? What is mu m? I took this mu o by mu r. So can I take mu o by mu r by mu o? Cut mu r. What is mu r? Is equal to 1 plus x, which is magnetic susceptibility. That's it. You see, mo m r, because they took this as r, or which is mu r. They took it as 1 and then they kept it there. That's it. And you can just read this and then you get the whole points. Look, magnetic susceptibility is different for all. Okay, the ones which are more negative, they cannot be strongly magnetized, but which ones are positive, they can be strongly magnetized. Now we'll go to our theory part, magnetic properties of material.